Welcome back to Decouple. Today I'm joined by a returning guest, James Krellenstein, whose previous two appearances and episodes on the past, present, and future of American nuclear energy have stunned myself and listeners with James' near encyclopedic knowledge and sharp analyses. Dylan, producer and co-conspirator here at Decouple, he's often reminding me to stop calling people savants. But perhaps I can just use it as an adjective, savant-like skills. I think got a lot of feedback from people saying, who the hell is this guy and how does he know so much? Some really respected people in the field at MIT and other places. So not to fluff your feathers too much, James, but made a big impact on those last two episodes and looking forward to having you back today.
Great. I'm glad to be here. And thanks for fluffing my feathers, I suppose.
All right. So the topic of the day. I'm labeling it small misunderstood reactors. How does that sound to you?
Maybe, yeah, sure.
All right.
Small misunderstood. I don't know how misunderstood they are, but we'll go into that maybe and see.
For sure. I mean, I have this is the need to categorize things, to create taxonomies for things in order to be able to discuss them. And we're pretty wonkish, so we like to go into details. And I think get frustrated by terms which are overly broad, insufficiently specific, and potentially misleading, particularly to people, with a cursory knowledge outside of the field. And I would say that, includes almost every single policymaker and government official I've ever run into. So it's a pet peeve for me, because of some of the misconceptions, such as the idea that everything labeled as an SMR can be produced like a Model T in a factory, driven to site, no need for any civil works, etc. And also some of the ways in which I think it's been a little bit self-defeating in terms of, the form of nuclear that has social license and therefore gets sort of a singular focus in policy circles where nuclear needs to be floated more as a trial balloon. And that often ends up, I think, creating some severe limitations. I got back from Australia about a month ago, where SMR has been sort of the focus, and the unfortunate consequences there are no currently deployed SMRs in the Western world, and that creates a pretty shaky foundation for that advocacy. So yeah, I mean that's where I'm coming from, where my frustrations are at. But we have a lot to talk about today, and maybe I'll just try and lay out a couple things, and I'm sure we'll deviate here and there, which I'm looking forward to. But I thought it was of interest. Great British Nuclear has sort of revealed a short list of reactors that they're interested in pursuing. All of them are small, at least. And they're all existing light water, boiling water technologies, which I think is very interesting because another sort of face of SMRs amongst policymakers, or the use of advanced nuclear often infers different coolants and moderators and so-called Gen 4 technologies. So again, I thought great time to touch on this, and really looking forward to hearing some of your takes.
Sure. So, I think it's a really, SMRs, I think, are at this point sort of more of almost a marketing term than they are a technical reality in a lot of ways. If you look at, what we classically, I think, want to think about in an SMR is literally like something like, as you said, a Model T or a Toyota Camry, that it comes off of a factory line and we just sort of plop it somewhere and turn it on. But except for the micro reactors, which are, below 50 or 30 megawatts, either thermal or electrical. Once again, this is where it gets very iffy, but generally definitely below 50 megawatts electrical. None of the SMRs, for example, that were in the sort of Great British Nuclear, which is I have a joke about that name, but regardless, those are not reactors that don't require any civil works. In many ways, I would like to think of them as really small, modularized, regular nuclear power plants. And I think that has advantages and disadvantages. But I want to pull back for 1 second and ask this very basic question, right? I think, a lot of areas in the world, right, especially emerging economies and lower income economies that really do need a lot more energy access, right? Do need for prosperity, for just increasing human health and well-being. In those places, we really do see grid constraints, right? The grids are not going to be able to take, if you go to a country like Rwanda, which has only a couple hundred megawatts, say, of installed capacity in total on the entire grid, you can't plop 1,000 megawatt plant down there and think it will work or it will be anything easy. But in higher income countries, and in particularly what we think of as the West, if that's whether that's South Korea, the U.S. or Canada, or Western or Eastern Europe, we have very, very large, generating assets. Many of them fossil, many of whom already have all the transmission interconnections already there, all the siting. And so it begs the question, what are we thinking about when we're trying to do SMRs? Because the whole reason why the nuclear power industry through the 60s, 70s, 80s, 90s scaled bigger is because there really are cost capacity scaling advantages that you get out of going big. And you see this in power plants just generally. It's why, despite the fact that we all are surrounded by small modular internal combustion engines called cars, we don't power the world when fossil fuels by just running thousands and thousands of 100 or 200 horsepower engines, right? We generally go to big 100, 200, 300, 400 megawatt combustion turbines or whatever the fossil asset, or bigger on coal. And so I'm very worried, I'll just be honest with you, that the obsession around SMRs is making us make some pretty questionable decisions about what the next reactor design should be. And I don't think that they are solving, I don't think I think SMRs, to be honest with you, are primarily, as we talked about in the last two episodes, they're a nuclear engineering solution to a financial engineering problem, right? And I don't really see that many other real benefits for SMRs for deploying for baseload power for what I think really need to decarbonize in the United States. Now, I realize it's a very provocative position, but I think I can walk through a little bit why I think that. And I think there's a pretty good case to be made. And just to finish up here, I'm concerned about what we've now seen in both the state of Illinois and in the state of California, where we had some heroic pro-nuclear advocacy done in the state of Illinois that got the legislature to overturn their moratorium on new nuclear power plants, and the governor vetoed it with the ostensible reason, this is what he claimed at least, that it allowed non-SMRs, that is regular large modular reactors, if you want to call them that, to use a Mark Nelson term, because it allowed those large plants and didn't only allow for small modular reactors, right? Literally, Jay Pritzker literally said, this bill allowed non-SMR reactors, and therefore I'm vetoing it. And then we saw a similar bill be introduced in the California legislature that would only legalize nuclear power plants for SMRs. So I think we really do need to start diving into the rationale between SMRs. And I'll just end with saying I'm not anti-SMRs. I'm certainly not anti non-light water reactor technology at all. I think they have a really important, incredibly important role to play. I just think that we have maybe undersold the advantage of the existing fleet reactors and the existing new larger reactor designs, and maybe oversold some of the advantages of SMRs.
Yeah, I mean, definitely that's been a big part of our struggle up here in Canada. Again, SMRs being the nuclear technology that are perceived to have social license, and a lot of our legislation, be it the investment tax credit, and others here, our fight at Canadian Nuclear Energy was to make it nuclear inclusive across the board, existing nuclear, CANDU nuclear, refurbishments, et cetera. And we've been successful in that. But I think the instinct of the industry was to sort of roll with that and say, well, we have license for this. And it's, really a brand new phenomenon, probably only a year old in Canada, that we're talking large again. So that is interesting. I mean, a couple of the rationales, and I thought this was a really interesting distinction. I think it probably we touched on it in an earlier conversation, but obviously this nuclear engineering solution to a financing problem, this difference between something being financeable and something being economic, I think are really interesting. So I'm wondering if you can expand on that a little bit.
Yeah, just right before I go, I say it's a financial engineering solution, a nuclear engineering solution to a financial engineering problem. But I think you hit also, as I also was talking about, it's also a PR solution, a nuclear engineering solution to a PR problem. It's a nuclear engineering solution to a political problem. And I think that this is sometimes, as I think I've mentioned, my father's a nuclear engineer. I've literally known a nuclear engineer very closely since the day I was born. Sometimes nuclear engineers view every problem as nuclear engineering problems,
Yeah.
and not every problem is a nuclear engineering problem in the world. And so when we have financial engineering problems, maybe we should try to do some financial engineering. When we have PR problems, maybe we should do PR issues and advocacy, not have a nuclear engineering solution to that problem. So going back to your exact thing, let's expand on this difference between financeability and economical. Right. So one of the problems that I've talked about, especially in the United States, is the way that we finance new nuclear power plants. Right. And for these large light water reactors that we've classically built in the US, actually the only reactors we've really actually built in the US for at least a very long time, you know, they are financed, as I said, as a system financing approach, where you basically have an entire utility pledge all of its assets and all of its revenue to be able to service the debt that is used, the bonds, for example, that are issued to build that large light water reactor. And just to sum it up, the basic problem is you're building a $15 billion plant or a $30 billion plant, hopefully a little bit cheaper, but in the double-digit billions, let's say for a 2-unit plant. I don't think we're going to get, no matter what we do, I think it's going to be double-digit billions for a two-unit, like gigawatt scale plant. The problem is that it's such a large amount of money that if the project fails, you really can threaten the entire utility or the careers of the people who are ordering that at the utility management. And with an SMR, as their name implies, they are just smaller, which means that the overall price tag is going to be much tinier than that, even if the price per megawatt is going to be more expensive. But because they make less megawatts, even though it might be a little bit more expensive per megawatt, the overall price is going to be a lot lower. So if you think about it from a corporate or a financeability perspective, they said, well, if this project fails, it'll be bad. No one wants a project to fail. But surviving a $1 billion or $2 billion project failure is much, much easier for a company than surviving a $15 or $20 billion project failure. And the problem is, as you just pointed out, that doesn't mean, however, that ultimately the power per megawatt hour, or even just on a nameplate adjusted basis, is going to be cheaper. In fact, we have a lot of reasons, and most of the rigorous peer-reviewed analyses that have looked at this have indicated that SMRs are likely going to be more expensive per megawatt hour or per megawatt electrical, just on a nameplate basis, than a comparable large reactor would be. And I think this is a real problem because ultimately nuclear power plants are creating people are going to object, but it is a weird commodity, but it is a commodity that is sold. And we're going to have a real hard time if the first couple of units that we are building are going to be producing power that is more expensive than we would classically think.
So I can see the rationale amongst the Western nuclear industry that it's better to build something than nothing. And if this is all we can build, and this potentially kickstarts a return to large nuclear, and that's, I think, some of the rationale up here in Canada is let's prove we can do it. I'm on board with that. I can't disagree with that. It is interesting, hearing and getting a sense of the Loan Programs Office mandate and what the limitations are, but seeing that there is hundreds of billions of dollars to throw around, that it couldn't happen in a more coordinated fashion, or there couldn't be, more aggressive financing of some large nuclear to keep the AP1000 supply chain intact domestically, et cetera. But given those confines, like I can see the rationale, and I'm not unsympathetic to it. Maybe maybe a reaction to that very quickly, but there are a lot of stuff I'd want to move on to, but just to that question of, as a means to kickstart a large program again, maybe the West just can't jump there.
Yeah. I think that once again, I am very happy that SMR projects are going to get off the grounds. In particular, I think the ones that are going to really get off the ground, like the BWRX 300, I think it, like all of the, because it's 300 megawatts electrical. So it's going to be an interesting thing to see if that plant in particular is economical compared to the large light water reactors. But here's where I'm, coming from. If you look at the LPO, right, and the U.S. Department of Energy more broadly, right, they have basically said that the United States, in order to achieve what is U.S. government policy by 2050, they're going to need 200 gigawatts, at least, of new nuclear power. In California, it's dozens and dozens of gigawatts. In New York State, it's dozens and dozens of gigawatts of new firm generation that is low carbon. And the only real firm low carbon scalable technology that actually has been deployed that we have right now, at least, is nuclear. There's carbon capture sequestration, hypothetically, for natural gas, but we've never really brought it to scale, and certainly not brought it to, providing 20% of the US electrical power, 70% of France's. So I'm looking at that, and I am sympathetic. I'm also sympathetic that there are a lot of places that we're going to need SMRs, by the way, in the United States. But when we're talking about the bulk amount of low carbon power, of firm low carbon generation that we need, the question that I have for everyone is, does it really make sense to be going 50 megawatts or 300 megawatts at a time, and possibly getting a lot of economic disadvantage, versus us really looking hard about, okay, we need to build the SMRs, but what is the policy decisions that we need to make to build the large light water reactors as well? And I don't think we spent a lot of time on that. And one of the things I'm just worried about, just to be honest with you, is we're already seeing some of these issues with SMRs happen. I think the SMR project that is furthest along in the United States right now is the Carbon-Free Power Project by UAMPS out in Utah, although it's going to be built in Idaho National Lab. And what we just saw, I think, is sort of giving credence to my warning a little bit, that, from 2022 to, January of 2023, the power price of that project more than doubled per megawatt hour. The estimated, it hasn't been built yet. This is just the paper estimate of what it's going to going from $60 a megawatt hour to over $119 a megawatt hour. And that's before any building has been done, right? Before we really actually have even the most detailed cost estimates completed. And I think this is, that project may not actually survive. That project may never actually get off the ground. And, I think we do need to be thinking, are we going to be ever able to get the economics of the SMRs competitive enough with what the large plants can provide, that we're able to launch this in a really sustained way that would get us to that point where we're delivering thousands and thousands of megawatts of new nuclear capacity. And I just, once again, the modeling is just not supportive of this idea that, these plants are going to be necessarily as competitive as the large plants are. And we're seeing that begin to happen now in real life as well.
I think there's a key difference between nice to have and need to have nuclear. And, when there's pragmatic reasons like energy security, again, driving decisions in Eastern Europe, that leads to the pragmatic decisions to solve the financing problem and do the most economic nuclear. So in my mind, that just doesn't exist in the US. It is interesting sort of seeing from the more, I guess, anti-renewable side of the nuclear advocacy movement, some sort of cheerleading on the spiraling costs of offshore wind. And I think some of those cost drivers are very much going to apply to new nuclear as a capital intensive resource dependent on a bunch of different commodities. So just a little side note there. I am, very interested in following along here because, over the last 10 years, there's been a lot of excitement about, again, so-called advanced nuclear, Gen 4 nuclear. I thought it was very interesting that the, 6 front runners in Great British Nuclear, reality TV show, the Great Runoff, whatever we want to call it, are all traditional light water technologies. So I think that sort of leads me to want to dive this issue a little bit more, talk about some of the drive behind the excitement for Gen 4 in the last 10 years. I think we're going to touch a little bit on sort of venture capital and how that's shaped a lot of, planning and imagination in the nuclear space. But first off, I guess, are you surprised by the shortlist for Great British Nuclear?
No, not for Great British Nuclear. I think, here's the, I call it sort of the Gen 4. It's kind of ironic. I call them the sort of back to the future reactors. Yeah. Because if you go back to 1950, right? Remember, the first, nuclear power generation was not by a light water reactor. EBR-1, experimental breeder reactor number 1, was, of course, a liquid metal, sodium, potassium, eutectic fast breeder reactor. And actually, that was the first reactor that produced any sort of meaningful amounts of electric power. This was way before we ever got shipping port or, a light water reactor nuclear power plant. These reactors have been around for basically from the birth of the nuclear industry to begin with, including molten salt reactors, right? You could go down the list, high temperature gas reactors. Here's the truth. We need advanced nuclear in a decarbonized world because light water reactors, by their very nature of using light water as a coolant or heavy water, water as a coolant, it gets very, very challenging to get to very high temperatures. It's not impossible, of course, but you really start, the pressure really, really begins getting very difficult to deal with water at much higher temperatures. And, a light water reactor is generally providing steam at 300 degrees Celsius, maybe a little bit higher than that. And for a lot of process heat applications, we're going to need to go to much higher temperatures. And if we actually get to a world in which we really do have a lot more nuclear than we do have now, we have fuel cycle needs as well to breed thorium or to really have a plutonium-based sort of fuel cycle. We're not anywhere close to that. So there's real important applications for advanced reactors. But my note of caution here is, we think of nuclear power as a firm, reliable source of generation because it is right now. But if you go back historically into the 60s and 70s, nuclear power, including in the light water reactors, were not particularly reliable. And the real technology that we got is we learned how to master that tech, right? We learned how to master that fuel, that coolant chemistry, that the fuel, the cladding and the fuel rod interactions. What is going on in a nuclear power plant and a nuclear reactor is magic. It is alchemy in many ways. You are literally taking atoms and you're splitting them into two or more daughter nuclei that may be unstable and then decay into a bunch of other elements. The chemistry, for example, just to give one example here, of this is really, really challenging and something that is not actually dealt with in almost any other place in chemical engineering or in chemistry in general. When a nuclear fuel rod chemically is one of the most interesting things that exists because you literally have dozens and dozens of chemical elements simultaneously being produced and popping in and out of, sort of going to the left and to the right on the periodic table as they go through beta decay or alpha decay. So it is an incredibly interesting, complex chemical environment that is not easy to master. And it requires a lot of, just to be honest, real world experience. And the issue that we have with a lot of these non-light water reactor technologies is not that they aren't great, not that they aren't extremely important to develop, is that they're not technologically mature in the same way that we see light water reactor technology. And this is not just hypothetical, right? If we look at the history of non-light water reactors, even among pioneering nuclear countries, whether it's the United States, Russia, France, England, right? We don't see the same reliability coming manifesting. If we take, for example, the biggest non-light water reactor power plant the United States has ever built, which is Fort St. Vrain, which is a high-temperature gas-cooled reactor in Colorado, right? Over the 10 years that plant operated, the capacity factor didn't hit 16% or cumulatively. It was 15.9% over the plant's entire life. Now, this doesn't mean that high-temperature gas reactors are bad. Just as if the operational challenges we had associated with light water reactors in the 60s and 70s doesn't mean light water reactor technology is bad. It means, though, that we do not have the real-world operating experience and understand all of those challenges that, to be honest, are almost impossible to fully exhaustively get through until you build one of these plants and turn it online. And what I would just ask us to realize is that I don't think we have prepared ourselves in the proper way to actually deploy Generation 4 technologies. I'll give you one very easy example. The West right now does not have a fast neutron source. We do not, a fast neutron source that is actually a nuclear reactor, ignoring accelerator-driven sort of magic or fuser-generated magic, right? When we're qualifying a new nuclear fuel, well, one of the things that you do is a test irradiation, right? You put it into a reactor, and you experience it, you expose it to a neutron flux that is going to be representative, at least we hope, of what it's going to experience in the commercial reactor. We don't have an operating fast reactor in the West. Outside of Russia and China, there isn't any operating fast reactor. There's hypothetically maybe one in Japan that hasn't been turned on in years. And just that sort of basic sort of testing ability, we don't have. So I'm asking us, we should be developing a very, very robust fast reactor development program or non-light water reactor, because they are so important and because they have a lot of advantages over light water reactors. But I think we should be clear about what these are going to be. These are likely we're not going to turn one of these things on and it's just going to be, 90% rock solid generation like we expect out of the LWR fleet. It's going to require some learning by doing in order to get to that expected reliability. And we're not taking the steps necessary to ensure that we actually get there.
Yeah, I mean, it's interesting going back well beyond nuclear to the beginning of the Industrial Revolution. I mean, our expertise at managing water under high pressure and using steam, I mean, this is hundreds of years old versus these more modern technologies. So it's not that the learning curve just began in the 50s and 60s. It has a far longer track record. So I do want to talk about getting from the lab bench to commercial operations, and I think you've talked a little bit about that from the operational side, and you're hinting at it in terms of what's required to qualify fuel, et cetera. But before we get there, I guess so much of the energy debate, the nuclear debate, is when we step back from it, especially non-experts like myself, it's bound in a lot of sort of aesthetic and psychological considerations and framings, and so I'm particularly interested in, again, the role of venture capital finance in some of the sort of paper reactor, advanced reactor type concepts, and sort of what's driving some of the thoughts here. And when I look at it, I see folks that have made a lot of money in tech in a highly disruptive industry. And maybe they've made their millions. They're maybe interested in making their millions or billions more, but they start to turn to these kind of broader existential problems facing humanity. Maybe it's climate, and they discover nuclear and they see how incredibly awesome it is. And I truly mean that in the word awe-inspiring, the alchemy, the strong atomic force, the incredible energy density, et cetera. And they're incredibly frustrated with the glacial pace of innovation, and think, hey, if I can disrupt this, I could solve this problem. Maybe I could make a pile of cash on the side. But I think there's this, incredible sort of frustration, and all these dumb nuclear engineers, they're messing around with the wrong technology. We proved that molten salts work in Tennessee, or EBR proves that just let's get on with it.
Nothing happened at EBR1 that was a problem. Anyway, sorry.
Anyway, so maybe riff off of that and what you've observed in that space.
Let me start with a story. Right. I have been a lover of nuclear power since I was 7 or 6 years old. And I still have the boy-like wonder with this technology. It is seemingly like anything else in the world that you put a bunch of metal rods in a tank of water, and that tank of water will just boil endlessly for years. That is something like it's like a Harry Potter or something. It is magic in the sense that the technology that we are utilizing in this entire field is the first time that man has captured the strong nuclear force and has been able to put it toward, sort of tame it and put it towards productive use, the strongest force in the universe. And that's why, the biography of people like Oppenheimer was called American Prometheus. It's literally, we took the strong nuclear force and the nuclear engineers sort of stole it from the gods. And sometimes it is easy in that magic to forget that a lot of this technology is to actually tame that magic is something that's really, really challenging, and that it's still really, really new in the history of humanity, right? It's only, December 2nd, 1942 was the time that we had the first self-sustained chain reaction probably on planet Earth since billions of years, since, Oklo, since the natural nuclear reactors. So it is now, if you now take that from where we are with tech, right? You have a bunch of people in Silicon Valley, as you said, who are in a field that is innovating really, really quickly, that has dramatic disruptive change on a couple year-long basis. And they look at nuclear power. And I actually one time was at a cocktail party in Silicon Valley. I think I've told you this story before, where you would talk to these Silicon Valley guys, and they would just be like, "You guys are literally using technology from 1953." Basically, which is the light water reactor technology. I didn't want to hint to them that molten salt reactors and sodium reactors are also that old, but their idea is, hey, this technology is so old, it has not been disrupted, really in any in their mind at least in any meaningful way for so long that there's gotta be a better solution than this. And therefore, they want to take that sort of Silicon Valley ethos, which so much of it is predicated in software development, where development, it can really happen iteratively, very, very quickly, very disruptively. And they want to apply it to nuclear engineering. The problem is that they're taking a software mentality to the hardest of hard tech, which is nuclear power, right? And the problem is as I was explaining, just the chemistry alone of these issues is very, very complicated and something that is very hard to understand without actually building and operating the reactor in the real world. It is not like running, a new, Python compiler or writing a new set of code or jumping from Fortran to Julia or something. This is something that really requires actual real world build experience and understanding the challenges that happen. And it's what Rickover talked about in the early 50s. That's why it's been since the early 50s in his paper reactor memo, that always a reactor on paper is going to be much better than a real world reactor. And the simple reason is that the engineers cannot foresee all of the challenges that are going to be associated with building a nuclear power plant in real life, because these challenges are so difficult to actually model completely on paper versus in real world. And that's why it's not like the engineers at General Atomics who put that Fort St. Vrain reactor together. They weren't aiming for 15%, capacity factor. They experienced challenges that they just did not know how to anticipate. And we've seen this throughout the nuclear development, space in every reactor technology, whether it's light water reactors, whether it's sodium reactors, whether that's, look at even the countries that are developing these non-light water reactor technologies, even the Soviet Union / Russia, which has been developing commercially sodium fast breeder reactors since the late 60s and deploying them, by the way, first at Shevchenko and then at Belarus, right? They are not deploying right now as their main technology the liquid sodium fast breeder reactors. Their main bread and butter reactor that they're building the most of are these light water reactors. Is that because light water reactors on paper are superior to liquid sodium fast breeder? No, they aren't. But they have the real world experience in both engineering, design, and constructability that gives it an edge. And what I see is a very different picture than maybe a Silicon Valley person does about the 50 years of using the same technology. What I see here is that we have 50 years of tech that has been built up by operating these plants that allows us, it's sort of the key to unlock that strong force and be able to turn it into useful work in an economical, reliable way. What I see is that it is amazing that we take the same plants that 40 years ago in the United States weren't breaking 50% capacity factor records, and now we're operating at 93%. That is technology. And that is innovation that has happened. It is just simply not maybe innovation in the nuclear steam supply system, but it rather is innovation in operations, in sort of fuel design and fabrication, and in the basic sort of real world experience of how do I actually operate this plant on a day-to-day basis. That's a huge technological asset. And when we sort of change the fuel, change the coolant, change everything else, we start breaking down and losing the tech that we have developed by operating these plants and are starting from more of a sort of blank slate. And that will maybe have advantages, but we have to be very careful to understand that we're going to have to build that other real world operational tech up, and if we're going to expect these plants to operate at a comparable capacity factor in economics.
I mean, this is reminding me a little bit in terms of, the category errors we're talking about, which are just, we're so prone to making as human beings. And talking about maybe the inertia of traditional technologies. I'm thinking about Václav Smil here and describing the prime movers that we rely upon and how old they are, how old the diesel engine is, how old even the jet turbine is. And these are technologies which are miraculous and have had iterative improvements and increased efficiencies and things like that, but they're not fundamentally different. And indeed, we haven't really discovered a new prime mover. I mean, I'm not an expert on this, but I think in the last 70 years. So there is, to someone who's looking to disrupt and for miraculously novel technology that's going to reduce costs or schedule by orders of magnitude, nuclear, I think, like those other prime movers, is going to end up being pretty frustrating.
Yeah, I think a really good example of this, to give you your industrial revolution example, is, we always like to think of nuclear power as the new fire. And it is, right? As I said, it's like this. It's not doing the chemical interactions that underlie combustion. It's rather using strong interactions and the strong force to generate power. And so if you just take that metaphor out a little bit. So, we have, as you said, in the Industrial Revolution, we had a lot of fire, right? Combustion-based processes. So first with a steam engine and then so on. But you would never think, if you built a steam engine, right, and you had a lot of experience building steam engines, that you're just going to trivially be able to build an internal combustion engine. But you're like, hey, these still both use fire, right? They're both using combustion to basically run the plant. That's sort of like, I like to make the analogy between a light water reactor and, say, a molten salt reactor. They're both using the same fire, that is nuclear fission, but the way they actually convert that into useful work that is used for an end use is very, very different. All the underlying engineering challenges are very different. And just as you would not expect to be able to just master building steam engines, that you're going to be able to simply switch over to build combustion, gas turbines or an internal combustion engine, we should sort of take it that the same way, that these are going to be challenges. It doesn't mean, by the way, that just because we had really good steam engines in the 1880s, we shouldn't have tried to build internal combustion engines. We should. We should still try to build gas turbines, of course, just like we should still be trying to build these Generation 4 tech. It's just that we need to be careful, I think, in understanding the relative levels of technological maturity that these different technologies have.
I mean, I think it's interesting, and I make this argument in relation to commercial fusion. It's insane that we went from the Fermi pile in 42 to shipping port 14 years later in 56. Is that just a testament to the times we were in, when the brightest minds? I think there's sort of the age of chemistry, the age of physics, the age of biotechnology. Like, we've been pursuing through these sort of scientific peaks of interest, and it's brought the brightest minds in. Like, how can this be so sluggish when, again, we moved from the Fermi pile to commercial nuclear power in just 14 years?
There's a couple things going on. One, as you said, if you think about these reactors, right? So we have the Fermi pile, CP1, Chicago Pile 1. We have, EBR1 in Idaho. We have submarine, the sort of predecessor of the Nautilus, pressurized water reactor being built in Idaho. We have Borax 1 being built in Idaho, right? And what do these all actually have in common? Well, in many cases, all of these reactors, which were experimental reactors, were built by the same teams of people, or involved the same team of people. Think of a guy like Walter Zinn, right? So Walter Zinn, of course, right, was at City College of New York in the 1930s as a physics professor. Fermi comes up to Columbia, which, down the block, and he starts working with Fermi, and is Fermi's right-hand man in engineering CP1, Chicago Pile 1. And then Walter Zinn, right, then goes out of the Manhattan Project, leaves the Manhattan Project, becomes head of Argonne National Lab. And at Argonne National Lab, Zinn is responsible for literally heading up EBR1, it was called Zinn's Infernal Pile, right, the ZIP, right? Then he was also responsible for helping build out at Idaho and got into massive fights with Rickover, but was literally on the team that was building the first pressurized water reactor and supervised the first building of the first borax experiments, the first boiling water reactor. So not only did you have in some cases, like a totally different governmental idea, support for building these experimental reactors. You had literally the same groups of people and the same teams and the same real world experience on how we're going to organize laboratory teams to be building these new reactor types. And you would just have the same people like, these grandfathers like Walter Zinn, who are just birthing new reactor types over and over again. And I want to go the one more step. We're forgetting that every single one of these reactors came out of government research and development labs. And they weren't immediately tried. No one tried to make the first boiling water reactor a commercial product immediately. Right? We built Borax 1 through 5, right? We built those test reactors, EBR1, then we built EBR2. We even tried to go right from EBR1 and EBR2 right to a commercial plant that was Fermi Unit Number 1 outside of Detroit. And that's a pretty disastrous operational experience.
We almost lost Detroit.
Well, not really, but yes, we had a core damage event at Fermi 1, and Fermi 1 was incredibly unreliable as a plant. What I'm not trying to say is that means that sodium reactors will never be commercialized. No. What I'm trying to say is if we have to distinguish between a science experiment and technology that we need to learn and master versus a commercially deployable tech that has to compete against other power sources on an open market. And this is not really, by the way, so if you want to go back to where you started this question, why did Great British Nuclear choose the light water reactor SMR tech? I think a lot of this has to do with exactly what we're talking about. The maturity of the SMR tech, whether it's the fuel, whether it's the operational experience of how you operate a boiling water reactor or a pressurized water reactor, that's not that far removed from the existing fleet's knowledge. And one of the things that I will say about this, fascinating to me for the United Kingdom, for the Great British people, right, is they rather uniquely right now have a nuclear fleet that almost all but one operating plant is not a light water reactor, right? They have one light water reactor, Sizewell B, but every single other reactor that they are operating is an advanced gas reactor, a high temperature, graphite moderated, gas cooled reactor. And they are not going to the next generation of gas cooled reactors. They are jumping back to light water reactors because the experience of the AGRs, while it's been not terrible by any stretch of the imagination, the capacity factor of the current AGR fleet is still not matching the capacity factors that we expect out of the light water reactor fleet. And even though we have all those advantages, including higher temperatures, the Brits are saying basically, hey, man, we're going to go back to the light water reactor because we expect that to give us better operational excellence than we've gotten out of 2 generations versus the AGR, but before that, the Magnox reactors of the high temperature gas cooled reactors. So I think that's kind of demonstrating the real value of the tech that exists in light water reactors, which is this half a century at this point of operational experience at commercial scale.
I think, part of the reason I care so much about this, particularly in a debate which tends towards conflict avoidance and all of the aboveism, and listen, there's so many gigawatts we need to build, let's just do a smattering of everything, whether it's renewables plus nuclear, even within the nuclear space, is this idea that we desperately need a win. And another loss is potentially hugely damaging. A discoordinated approach is damaging. Non-standardized approach, not learning from the successful lessons of contemporary and past nuclear buildouts. Something that drives me crazy in Canada is, in a province of, I think, 800,000 people out of New Brunswick, not one, but 2, again, Back to the Future reactors or Gen 4 reactors are in some stage of planning. And again, this is a province that runs a single CANDU 6 unit. They run it terribly, unfortunately. Sorry to my Point La Pro listeners. I really hope that things can improve there. But that this is going to be some center of miraculous innovation when the French program at its height with Super Phoenix fizzled. The Japanese program with Monju fizzled. Massive state-backed enterprises that 2 tech startup companies are going to be able to get it right, get it operating, get it economical. Just seems so fanciful that I wonder why it's still being taken seriously.
So I want to, it's a really interesting question, right? And I agree with you. In my mind, what the world nuclear industry, and maybe outside of Russia and China, let's put it this way, what we really need right now, as you said, is a win. And the question is what path do we take to get that win? And I think all of us are sort of realizing if we can get a couple wins under our belt, then this world of the hundreds of gigawatts that we need to meet suddenly becomes realistic, that we're actually going to be able to start building that. And I think there's a lot of people who think that throwing away the old tech and starting on something newer, quote unquote, simpler, smaller is the way to do it. And I realize that this is a controversial perspective. I believe that actually the most likely chance we have for a win is using the stuff that we've already done, that we have all of the build experience in, that maybe it wasn't a great build experience, but we've done it, we've gone through it, and we've got the plant operating now. And most importantly, in some ways, when we turn that plant on, forget about the build experience, which is it's going to actually reliably generate power and be able to service the debt that it accrued to basically build that plant. And that's really, really important. And you brought up Super Phoenix, right? Which for listeners who don't know, was a French breeder reactor, a big 1,300 megawatts electrical breeder reactor, huge, in France, that was built, started in the 70s and was finished in the 80s. And, the French at this time were really, building a lot of nuclear. They had a very, very established, nuclear suppliers and industrial capacity. They had a great educational system that was minting new nuclear engineers. And what happened in Super Phoenix is, in some ways, exactly what we would expect. But it turned out to be a disaster for it. What happened is when they first turned on Super Phoenix, right, it had months and months of outages, right? In 1986, when we first connected Super Phoenix to the grid, right, it really had a capacity factor that was extremely, extremely low, right? I believe below 30%. And we had major operational outages that were caused by leaks in the intermediate heat exchangers, right? We had oxidation of the primary sodium. We had cracks on the external fuel storage drum that basically was what you took the fuel assembly after you defuel it into. And this caused huge amounts of outages, right? The plant wasn't operational for literally a decade, right? In any true sense. It was going on and off, and also in a famous incident, the turbine building literally collapsed due to heavy snowfall, which I'm not so sure you could blame that on it being a new sodium reactor. But anyway, what this gave was huge amounts of opportunities for opponents of the breeder reactor program, even in a relatively pro-nuclear country like France, to basically say this is just a money sink, an absolute abject debacle over and over and over again. And so even by the time that they had really likely, hammered out a lot of those kinks by the mid 1990s, and we actually had a run that was at a relatively high availability, maybe even above 90%, the political opposition to this was so great that they killed the entire program. And Super Phoenix was retired in 96 and never really generated very much power at all. And what I worry about, what the lesson of Super Phoenix to me is not that, once again, we shouldn't try to build sodium fast breeder reactors, but we should manage expectations, and we should be clear that we should not expect, when we first turn on these new technologies, that they're going to really, really perform like the light water reactor fleet does. And what I worry about is that we are not developing that infrastructure right now, right? If you look at the budget of what, just in the 1960s, the Atomic Energy Commission was just spending on new reactor development. We were spending, in inflation-adjusted terms, by 63, 64, even past the peak of new reactor development, $4 billion a year on just developing new reactor technologies at the AEC, right? And pioneering them and building them out in Idaho, right? Right now, that is larger than the entire budget of the Office of Nuclear Energy and the Nuclear Regulatory Commission combined. Forget about what we're spending on new nuclear reactors. So when we're talking about building a new technology like this that does not have that operational experience, I would question to my venture capital friends, it's great that you're putting that money in. It really is. But how are you going to get through? Let's imagine you even get to the point where you're building the reactor. How are you going to get through commercially as a private investor? How are you going to justify to the investors that maybe put the money in to build that plant, that couple year period where we're not going to expect the plant to work so great. And that is my concern right now. It is not, once again, that we do not need these reactors. We do need these reactors. We do need disruptive startups going through. But how are we going to actually do this on a full private model without government support when it's going to be very hard to get these reactors, to be generating a lot of power? Likely, we don't know. Maybe I'm wrong, and we're going to turn them on and they're just going to be perfect out of the box. But I don't think that has ever happened before.
I think just because there's so much hype about liquid thorium and molten salt reactors that we kind of have to go there a little bit. We've been talking a bit about the sodium moderated reactors in France.
And they're not moderated.
Sorry,
they're fast
cooled
reactors, right? Yeah.
Oh my God, I knew I had my foot.
Well, there are sodium thermal. There are moderated like halum, that are graphite moderated, sodium cooled. So yeah. Anyway, sorry.
My bad. But I do appreciate the correction. Yeah, so in terms of the molten salt program, again, I think one of the smartest anti-nukes that I've come across, MB Ramana, he does a lot of pushback on SMRs and on molten salts in particular. But one of the points that he mentioned, and I think it's a fair point, is similar to this theme we're discussing. This is referenced as hey, we've done it before. Why aren't we just doing it now? 225 outages, only 58 were planned. This is not mature technology, and I think belongs in a national lab to keep working out the kinks and scaling up slowly before jumping to 300 megawatts, gigawatts scale. I don't think anyone's talking about a gigawatt scale molten salt reactor, but can you talk a little bit more about that experiment and maybe temper some of the expectations while preserving some of the excitement about the end place of where this technology could belong?
So for molten salt reactors, so for people who don't know what an idea of a molten salt reactor, and I'm going to be talking here not about like a Kairos-like design where you have solid fuel but a molten salt coolant, but I'm going to talk about a molten salt with a liquid fuel, right? So what that basically means is that unlike a nuclear, like a classical light water reactor, or even a fast reactor where the fuel is solid, right? It's either uranium dioxide or metallic uranium or triso, sort of pellets. Instead, in a molten salt reactor, what we do is we put the fuel in solution as a salt with the coolant. And there's been two examples really of this, right? Which, as you mentioned, one was the molten salt reactor experiment at Oak Ridge. And another one before that, actually, was also at Oak Ridge National Laboratory called the Aircraft Reactor Experiment, or the ARE. And the aircraft reactor experiment was a 2.5 megawatts, full power reactor built in 1954, went critical in 1954, and it was moderated. And here's the problem with that. You remember how I was talking about, or not the problem, right? Once again, I am not anti-molten salt reactors, but let's just go back and actually look at the operational experience of these reactors. Remember when I was talking about before that it's sort of like, Dmitry Mendeleev, eat your heart out. A nuclear fuel rod is we're generating all these different chemical compounds constantly as fission products or as, decay chain intermediates from those fission products as we go down the decay chains. So you literally have dozens and dozens of chemical elements going on. Now, in a uranium dioxide fuel pellet, generally those are in a solid, crystal lattice of some sort that's basically keeping the sort of different compounds all fixed together in a solid. They're not sort of messing around and interacting with each other. With a molten salt reactor, as just an example, what we're doing here is we're taking that all those fission products, all those decay chain intermediaries, and we're putting them into in the liquid fuel, and they're all interacting with each other, which means that the chemistry becomes non-trivial very, very rapidly. And as one friend one time said, this is the most exotic chemistry that has ever existed on planet Earth in some ways. So if we look at and we've only built, to my knowledge, only 2 molten salt reactors that I just named actually ever went critical and actually turned on. And one of the more interesting things, in addition to, the aircraft reactor experiment was 2.5 megawatts thermal, right? And the total run generation was 96 megawatt hours of energy complete. So if you just do that math, that means on a full-time adjusted basis, right, the plant was literally running for an equivalent of 38.4 hours at full power. Now, it was actually running for a lot longer at lower power, but that gives you how little of a experience that we actually have operating these plants. And then in the molten salt reactor experiment, as you mentioned, right, the full power output equivalent was much longer, right? We had about 9,006 hours of full power output equivalent on the first run, and about 2,549 hours on the second run. But still, in total, we are looking at less than 2 reactor years of total, full power equivalents on just these 2 small test reactors. And what I would give you, just to give you an exact example of what I'm talking about, these unforeseen challenges. When we looked at what happened here with the molten salt reactor experiment, when we turned it off, and it turned out the decommissioning of that plant was not easy, but it is done to my understanding. One of the things that we found was a form of corrosion called intergranular cracking, and it turned out which causes embrittlements in the metal surfaces that were exposed to this fuel salt. And it turned out that the culprit of this embrittlement was an element called tellurium. Now, tellurium, for those who don't know, it's atomic number 52, right? It's a really rare element. It's about as rare on Earth as platinum is. And it's something that we don't really know that much of the chemistry of because it doesn't really have that much interactions. We don't, use it very much. There's some niche applications. Well, we make tellurium in this sort of nuclear fission alchemy soup. That is the product of driving fission products. And it turned out this tellurium interacted with components of the piping in the molten salt reactor and caused severe, embrittlement over the entire reactor, exposures. Now, what is the lesson that I'm trying to get out of it? It's not that we can't solve tellurium-induced intergranular cracking. It's that this was a completely unexpected, complication of the reactor design that no one at the drawing stage or at the planning stage ever anticipated. And it could have been a very, very severe operational challenge if we tried to bring that reactor commercially. This is, of course, why we have national laboratories. This is why we run science experiments, is to figure out what these real world challenges are. No one would have ever anticipated that tellurium was going to cause intergranular cracking in the particular alloy that was used in this piping, but it did. And that's the exact example that I like to give of real world challenges that you don't necessarily stumble upon until you operate the plant. And it's just not true that we've had that much operating experiences with molten salt reactors. There's 2 examples of this, right? 2 reactors that have gone critical. I think the Chinese are building one more. It's not clear if it's ever gone critical. And why are we saying that this is just going to turn on and just be a complete, walk in the park? And I'm sure I'm about to get a huge amount of hate about this episode. I have to say, I am just bracing myself for the hatred that's about to happen. But what I'm trying to say is I'm not trying to be a party pooper. I'm just trying to say, let's set ourselves up for success. And that means being reasonable and realistic about what the challenges we are going to face with really new advanced reactor technology.
I mean, I guess we just finished last week our episode with Jacopo Bongiorno about the cost of nuclear based on the excellent MIT report. And what he was saying, at least in their study and their modeling, is that 20% of the overnight build cost is in the nuclear steam supply system or whatever. I'm not sure if they were looking at advanced reactor concepts, but in any case, a vast amount of the cost is in construction. I guess charitably, people making arguments for the rapid deployment of Gen 4 technologies and molten salts, for instance, say, hey, it doesn't require all of as much civil engineering because it's not a high pressure system. What do you think about some of those arguments? Because otherwise, I think we're stuck with trying to attract VC money to some really boring stuff, which is like, let's generate incredibly excellent institutions and incredibly well-trained people that take 20 years to get up to snuff. Like that's not something that's like a VC deliverable, I feel, or something that's sexy. Or let's develop better steel bricks. I don't know what, some kind of revolution or disruptive construction experience. And I think Jacopo's report also looked at like the productivity within a variety of sectors and just how construction has flatlined or gone negative compared to sort of manufacturing processes. I'm getting too broad here, but reflections on that scrambled egg soup of a question.
So there's three things going on here, I think, and we should decouple them. So the first is on the civil engineering builds, in particular, concrete, reinforced concrete, and that sort of issues, in addition to improvement, excuse me. So the pressure thing, right, is generally what we can associate that in the first, if you first think, in the first thing, what we think about is, when you're building a nuclear steam supply system on a light water reactor, we're operating at thousands of pounds per square inch in order to maintain the reactor, the reactor coolant system at a high enough pressure that we, get to we get above 100 degrees Celsius for the boiling point of water, right? And you need that obviously for the thermal efficiency of the plant, among many other things. So it really does require a huge amount of welding and very, very, thick piping, and it's not trivial by any, and even, things like, the sealing of the reactor coolant pumps all of a sudden is not a particularly easy thing to do, but we've mastered it. But that would be, as you just said, as Jacopo said, that's 20 to 25%, 18% sometimes, depending on what model, of the actual NSSS costs, actually of the actual power plant costs, is actually the NSSS. One of the hypothetical advantages that you can get out of having a much lower pressure system is that, say, for example, the design of the containment building needs to be much less, or sometimes you don't even need a containment if you're in a really advanced. You can have what's called a functional containment, depending on your fuel types, if you're using something like triso, right? You can maybe eliminate a lot or really reduce the price of the containment building, which is a major cost driver and a major cost of that civil works, if you really improve that. That's definitely true. I think it varies from technology to technology in Gen 4, but, it is true. And that's why I'm not anti Gen 4 technologies by any stretch of the imagination. But what I want to sort of turn back on you, though, is ask you the question about what Jacopo said about the cost drivers. And now let's go back to the light water reactor SMRs that we are building. Well, one of the things what's really, really interesting is if you look at the historical drivers of the low productivity in Western construction, which is hypothetically what these plants are designed to address, right? One of the problems that we've had in new nuclear builds is that just construction productivity has been very, very low, especially compared to manufacturing productivity. Well, one of the things that's really interesting is you actually look at the data and say, well, okay, let's actually now compute on a megawatt basis how much labor that you're going to need per megawatt hour in direct labor. So like ignoring QA, QC, management, but just actually like craft labor and manual labor is building the plant. And then you do this math, and there's really good peer-reviewed data actually from MIT, from Robbie Stewart and Kurush Shervan and Jeremy Gregory, right, who really actually analyzed this in a very, very rigorous sort of publication, and got it published in Nuclear Engineering and Design in 2022. What they found was, for example, for a BWRX 300, right, compared to an AP1000, you need, for the BWRX 300, 2/3 more man-hour, or people hours, human hours, labor hours of direct labor per megawatt electrical than you would for an AP1000. So here's an example of where I'm worried a little bit, right? We know for a fact that, craft labor and manual labor productivity has been low. The input amount that we really need is going to be a very cost determinative thing, as Jacopo was talking about, because that is the major driver in many ways of construction cost, is the actual getting the workforce out there, getting enough people, and so on. And we are choosing designs that per megawatt electrical are requiring a lot more labor, at least on paper, than the larger reactors that we've had in the past. And what worries me about this is that this is a perfect example of why you generally try not to solve financial problems with nuclear engineering solutions. Because each time you try to solve one problem by changing the nuclear engineering completely, we introduce a whole new set of new challenges. And what I would just like us to think about is, let's look at the real underlying causes of cost escalation and try to address them. And I'm not so sure, I'm not convinced that doing this with increasing the amount of labor hours, direct labor hours per unit megawatt, is the right direction for our field, given the challenges that we have associated, that we've had historically. And that's what I'm just trying to put that out there. I love the BWX 300. I'm very excited it's getting built. I'm not trying to say we shouldn't try to build it. I'm just trying to say we should be looking at the cost and benefits that we have of these new solutions, and realizing that sometimes it's not all better always.
A couple thoughts there, I guess. I mean, one is, these labor hours, absolute versus relative. And I mean, on an absolute basis in terms of getting that, not on a megawatt hour basis, but just in terms of getting that project done, there'll be less labor hours and it'll come on earlier. Another argument you hear is that, well, the SMRs will start producing electricity earlier than a large build, and therefore be more financeable and ultimately be able to pay back a bit quicker. I think there's a really absurd example of this, which is with NuScale, where you need to build an absolutely enormous civil engineering project and civil works to, and you're starting to pay that off only, 77 megawatts at a time as you get these units in. That almost seems to work counter to that argument. But do you have any sympathy to that idea that, you'll get operating quicker and be able to pay back your debts quicker, and that'll kind of make up for the difference?
I hope that's true. And I think it probably will be true. But the thing that I don't understand about this is we have built, in modern times, modern large light water reactor designs very quickly, right? And I'm just, going to go, people who know me know exactly the example I'm going to give. Look at the advanced boiling water reactor builds in Japan, right? We were building those on the order of, 36 to 48 months, right? From first nuclear concrete to commercial operation, right? And the only difference is that we got 1.25 gigawatt electrical out of that, or no more, a little bit more, 1.3 gigawatt electrical, out of each reactor built, rather than 200 or 300 or 50 or 75. So yes, I think that it is a good thing to go faster in building the smaller plants. However, I am not convinced that that is an intrinsic advantage of smaller plants, because we have obviously built, and many times over, large light water reactors as quickly. And I think in a world in which we can build small modular reactors fast and we can build large modular reactors fast, the large modular reactor wins. And I think that is the challenge. What we need to be figuring out right now is, well, how do we build how do we replicate what the Japanese did in the 90s and in the 2000s, right? Which is not that long ago. This is not 1970 whatever, right? This is literally, I was alive for these things. I mean, very young, but I was in middle school by the time the last ones were really being done. This can be done. And I think the question I would like to ask you is, do you think it's more likely that we're going to be able to build a first-of-a-kind small modular reactor faster than if we try to really figure out how to take a large Generation 3 reactor that we've already built and already operated and already had a running supply chain, already had a regulator? If we really tried on doing that, which one do you think would be a higher probability of being faster? And my money would be that we could do better by betting on something that we've already built. We've already gone through those kinks, and now we just need to institutionalize that learning and put it down to go faster. And the second thing I just want to be honest about, be clear about, is that yes, it's really great to get a power plant on very fast, but ultimately that power plant has to be able to be competitive over 40 or 60 or 80 years. And that is ultimate. If we're building plants very fast, but they're going to be very, very, or much more expensive relatively, I think there's a trade-off here that we have to figure out. And I'm not so sure we're paying enough attention to that trade-off that we're getting.
So I guess moving towards closing here, the biggest question, and maybe a bit of an unanswerable one, but I'm interested in your thoughts about this, because we've been doing a lot of, sort of diagnosis and working our way through the problem. Thinking about solutions, particularly when it comes to finding finance, keeping the interest of VC finance, as we also try and have a more organized, perhaps informed direction coming from the state as well. How do we get there in terms of the kind of the solutions that you're sympathetic to? What would that look like in terms of the not the nuclear engineering solution to some of the problems we're discussing, but this question of if we're talking about building large again, if we want to try and build another AP1000 again, and it's not going to happen through the Loan Program Office or something that's more top down or vertically integrated, is there any kind of novel way in which to organize that or build, focus on that question of constructability, of institutional excellence? Like, how is that possible in the West or within the US in particular?
So there's three things I want to say, right? The first is, I know I've sounded a little bit like a downer. That is not about Generation 4 and advanced reactors and even SMRs. That is not at all my intent, right? I believe that SMRs are vital and that they will play a vital role in decarbonization. I also think that Gen 4 advanced reactor technologies are going to play a vital role as well. And to go to your question, what are the solutions to maybe some of the challenges that we've been talking about in that space? Let's start there. And I think a perfect example of this is we need to see better advocacy for things that Generation 4, particularly in the fast neutron spectra, what they need, right, in order to qualify their plants. And, the one of the answers I have for all of this is, Idaho. I mean, it's Idaho, baby. It's not just potatoes. Like so much of the modern reactors technologies that we talk about today came from Idaho, came from what is now Idaho National Labs, was the reactor test station. And we really do need to bring back the idea of what we are talking about when we're talking about building advanced reactors. Building prototypes up at Idaho is a really, really important thing. And that is going to lead the pathway, in my mind, to effective commercialization, because you don't have the anticipation when you're building a government reactor experiment, that reactor is going to be as reliable as a commercial plant. And we already are seeing some of the really smart, really great, new reactor startups like Allo Atomics. Right, what they're basing it on is they're basing on the Marvel reactor. And the Marvel reactor is a test reactor that is being built at Idaho National Labs. And that way they'll get that real world experience on a test reactor and be able to translate it into a commercial product, hopefully. But they're not anticipating the first of a kind reactor. They're not going to have any operational challenges that we're going to solve right out of the back on the commercial private market. The other thing is just increasing the budget of Idaho and getting congressional support in the US, for example, for something like a fast neutron test reactor. There was a proposal that both the Trump and Biden administrations have been behind, which was something called the Versatile Test Reactor, which was going to be a small version of the PRISM reactor that was going to basically be built at Idaho to basically have that fast neutron irradiation capability and test reactor capability that does not exist currently in the Western world. And if we're really going to be serious about building these fast reactors, that's a bare minimum. We really do need test reactors that can actually, irradiate, say, fuel samples at a spectra that is, somewhat comparable to what we would expect the commercial plant to be operating at. So I think that's a really, really important, just sort of bare bones. Let's set the table for having a successful advanced reactor market and development. And that does mean, I think, a little bit more advocacy, especially as nuclear advocates become more numerous in number, pro-nuclear advocates, and more sophisticated. Let's try to build more, advanced reactor experiments and build test reactors that really can pave the way for effective commercialization, and commercialization that is likely to really pave the way for a commercially viable and successful product. The second question that you asked is that how do we deal with a large light water reactor problem? So I think there are a lot of policy issues. I mean, that could be a whole nother episode that we talk about. But one thing that I would love to just say at the bare bones is I think we have to have a little bit more of a data-driven discussion about SMRs and about what we're expecting out of them, where it makes sense to deploy them, and where there's some questions about whether they deploy them. Right now in the United States, there are gigawatts and gigawatts of new, large Generation 3 reactors that have full licenses, new, that could start building from an NRC perspective tomorrow. And, I am not necessarily the most critical person of the NRC, but, going through the NRC combined construction and operating license process is way too long, is a huge burden on everyone. Right now we have gigawatts of plant at places like Turkey Point outside Miami, where we have 2 new licensed AP1000s that if we decided on and advocated for, we could start building tomorrow. The NRC has granted a COL that is active and operational. And we should be thinking about these opportunities that we have to be building new plants right now and just advocating and talking about it more and talking about the advantages of it and having the difficult discussion that we need to have about what happened at Vogtle, what happened at Summer, and actually have that conversation in a real objective way, not in a way that is, oh, it's the NRC's fault, it was, everyone else under the sun. No. A real root cause analysis about what happened at Vogtle and how will it not happen again. And in my humble opinion, when I've looked at this problem, and I've spent months and months and months looking at what happened at Vogtle, what I take away from that is, yes, Vogtle was kind of a little bit of a disaster, but my general takeaway is that all the challenges that we faced would be unlikely, in some cases impossible, to happen again. And that is something that I wish that we talked a little bit more about. We dealt with the PR challenges, let's call them that, of Vogtle and Summer, not by a nuclear engineering solution, but regular old PR. Right? Let's talk about, explain what happened, level with people, take responsibility, but also explain to people why this will be different, especially when we have so many sites that the NRC has already given a full license to begin constructing and operating those reactor designs, and where we have reactors being ordered in Poland to that exact type, and we have the real world labor experience. Let's try to sell that a little bit. Try to talk about it with pride and understand that it's not every solution is going to be solved by a nuclear engineering problem. Is that a cop out, or do you? I
mean,
I just don't. Yeah, go ahead.
It's going to require, I think, a lot more elucidation. But I think that question of where does the VC money go? Again, with that psychology of disruption and that bias towards, let's find again, maybe a back to the future solution, but something very different than what is currently there to see if we can disrupt this aged, slow-moving technology. If what's required to get from the lab bench or the laboratory to commercial operations is a lot more time in the lab or the national labs, that's not really a place where you're going to earn a bunch of returns for VC, in terms of investing in the versatile test reactor, for instance, right? So how does VC or that private capital that's wanting a nice return get that return and stay interested in nuclear if this stuff is still the kind of disruptive stuff that they're attracted to because of that base psychology is decades away, or at least a decade away, in terms of getting to reliable commercial operation where you can pay back the principal?
So, I think the model for this is biotech, right? So if we look at, biotech is a much, much larger venture capital market than than nuclear is. I mean, probably by an order of magnitude, if not 2. That model is very much based on what in my mind, that's very analogous to what the nuclear sort of VC model should look like, right? In that model, what you have generally is you have a huge amount of government funding here in the U.S., like NIH funding, that is exploring the basic concepts, that sort of bench research that is happening, right? And then a scientist or engineer, a scientist at a university will discover a promising, let's say, signal transduction pathway where that through this, government support, and it doesn't make sense, as you just said, for VC to just be supporting random researchers at universities. But what happens is those random researchers, right? And I've actually done a lot of biological research in my previous career, right? They will discover basically a promising approach, right, to say curing a disease or developing a drug. Right. And it's at that point that the VC starts working on them with the commercialization. And what I think we need to be looking at is exactly more like Allos in the world, right? Or Project Pele as another example, where we have the Department of Defense basically building the first prototype reactors. And then we have companies like BWXT and X Energy who are going to be building those prototypes. We have then commercial funding to basically take them and commercialize those first of a kind prototype reactors. And that's a really comfortable place for VCs to be. It's a really comfortable place for the industry to be. And I think it would be really, really great. Because one thing the government isn't good at is commercializing technology, right? And we have this real ability to, I think, work synergistically. But I think we do need to understand a little bit more, maybe a little more humility in understanding that generally these things are very, very challenging engineering wise, and we are going to encounter almost guaranteed challenges that we did not foresee at the paper planning stage or in our computer models. And it's just building in for that and understanding that, hey, we should have maybe a matching model with the DOE, where we have DOE put in some money, we have the VCs put in some money, and that those first prototype plants really are going to be a shared, endeavor between private investors and public backing. I really do think this is important for a technology like nuclear, where it's really, really hard, I think, to get it right the first time out of the box. And I think the VC, injection into the nuclear space is fantastic. It's giving so much vitality and energy and getting young people so much more involved in the nuclear sector. I just think we need to do some policy tweaks here, right, to really make sure that we are planning for what I think we all anticipate, that the first reactors are not going to be perfect out of the box.
I guess the question is, and any kind of analogy is imperfect. And biotech does take a long time. Clinical trials take a long time. But at the end, you often get not often, but when you do, and you strike it rich, when you get a blockbuster drug, there's just an enormous payback on something which is...
that's the VC return model, right?
Totally. But you're producing, say, a pill, and that's, nothing like a nuclear plant, and it's mass manufactured in highly productive facilities. I question your analogy there, the utility of that analogy, just with, again, the slower pace of development in nuclear and the end product that you're deploying and its ability to generate massive returns.
Well, I think this is where we do get into the advantages of particularly in the microreactor side, on truly manufactured mobile reactors, right, which is going to be small, but those hypothetically could be mass produced. You could get a manufacturing license from the NRC. They're not going to be like a small molecule or a monoclonal antibody or something, but they possibly could have not. Once again, no metaphor is perfect, and I think this is a limitation. But they really could be in a much more manufacturable space. And I think the question that we all have to ask is, well, what are the challenges that we're going to be associated with building those small reactors? And what are the applications that they're going to be? In my mind, it's going to be unlikely, but other people very much disagree, and very smart people, that we're going to have a world in which it's all thousands of small little microreactors lined up. I don't think that's what's going to happen, right? But I think there's going to be a huge application for microreactors at remote off-grid applications, for mining, where diesel fuel is basically used right now, for military operations, as an example, for forward operating positions. I think there's a huge possible place, and that's a very big market that could be disrupted. So I think, yes, there is there is a breakdown there. On the other hand, I think that if we get on the larger space, if we really do get something that is systematized and productized in the way that we can build and deploy it, and we can really get reliably 3-year or 4-year builds out of it, we build combined cycle gas turbines, right, pretty quickly, and they're 400 megawatt plants, and we snap them together in a couple of years, generally, and sometimes even faster than that. I really do think there is, if you got into that place with a mature technology that really was able to do that, I really think we have the ability to have a VC-like return, right, on that. I'm just not so sure that first gas turbine, quote unquote, or that first reactor module that we build is going to be commercially viable. And the question that we as VC, if you're a VC, need to ask yourself is, well, what is the plan for getting through that death zone, right? That death zone where the first product has been built and it's having a lot of operational challenges that weren't anticipated. And there's probably a light at the end of the tunnel, but how do we drive through that tunnel and survive commercially through that tunnel? And what I would just say is that, the challenges that we're talking about with these new, they go from small to large, right? Even the small, the Army in particular had huge programs in the 60s to develop really mobile, like ML1, which was literally on backs of a couple trucks, right? To basically build small little reactors to be deployed in forward operating positions in the case of ML1. What we saw with ML1 is that plant never, I think, got above 60%, of its outrate, of its, design power. Forget about anything else, right? We really saw major challenges with getting, for example, ML1 from a design perspective done. In fact, I think an Army study concluded that it was going to be 10 times more expensive than deploying diesel fuel for that first reactor. And so what I'm trying to say is maybe that ML1 technology actually, I think it's pretty promising, but it's going to require a lot of tweaking to get it to a commercially viable position. And how do we, as in a full private market, how do we fund that tweaking that needs to happen and keep that plant alive? I think one of the things I do not want to see happen, and I'm worried about, is the same thing that happened in so many of the large light water reactor builds where we abandoned the project a third or a half of the way, like a plant like Marble Hill or Whoops 135, right? 4 as well, right? Where we literally just have these massive bulking, or Cherokee, right? We have so many, America is littered with half-built nuclear power plants. And what I'm trying to say is I believe in this technology. I believe that these small reactors and microreactors are going to be incredibly important. My question to you is, and to all of us, and I don't have the answer, is how do we have a way, and it could be government funding, there could be another alternative, where we can make sure that once we get through the hard stuff and build that first one, when we have the anticipated operational challenges, how do we see it to the end to actually finish that commercialization process?
Right. We should leave it there, but just one more question, and this doesn't apply to the potential higher value applications or products of nuclear, like process heat, but that challenge of getting a big return on something which is undervalued, which is baseload reliable electricity, which is obviously not rewarded the same way that a natural gas plant is in a competitive market. It is interesting to start seeing, especially with the thoughts around how energy intensive AI is going to be, and Microsoft looking for potential PPAs with nuclear, citing nuclear microreactors at server farms. I mean, baseload is kind of cool. It's back, both because we've realized that it's not a myth, but also there's value to having really reliable electricity, and that value is higher as we head into increasing grid fragility. But yeah, in terms of that question of is producing baseload just such a disadvantage to nuclear in terms of generating good returns in current market structures?
So I think one of the really interesting things that we have done from policy perspective in the United States is introduce, sort of put on a more level playing field than ever before, nuclear generators alongside so-called renewable generators, on basically giving the economic incentives. And one of the things that gives me the most hope about actually dealing with this problem is the production tax credit that we have built into the IRA, right, for new nuclear generators as well as existing nuclear generators. And that PTC, right, it gives basically a big incentive, if I may be so bold, for nuclear baseload to be built, because at $15 per megawatt hour, a PTC, you are all of a sudden, if you're able to consistently, rack up those megawatt hours, well, you're just going to get a very, very big rebate check at the end of the day, even if, right, the wholesale power markets aren't properly valuing your price, the price of the reliable baseload power that you're generating. And it's one of the reasons why we've seen this work, even in a state like my own, like New York State, right, which is a so-called deregulated power market operated by the New York Independent System Operator, right? Even the small plants like Gunay, upstate, which is like a couple 100 megawatt little solo 2-loop pressurized water reactor, has been kept online, even in a very highly competitive wholesale power market, by a state PTC that was put into place. And I think having a federal PTC is really going to change the name of the game on actually making nuclear power competitive. Now, in all honesty, we're kind of begging the question. The better question we should be asking ourselves is, well, how do we redesign our wholesale power markets such that they properly value the price of firm, clean, bulk generation. And I think that is another whole nuclear advocacy. Maybe it's some sort of tax credit, but I think we really do need to be looking at the market designs in the deregulated markets of how we're going to properly value this. Because I think it's becoming increasingly clear that our current models, especially in a place like an energy-only model like ERCOT, like in Texas, where we don't have any capacity market really, we're not properly valuing the social and economic benefits actually of having reliable, clean baseload power. And I think that, maybe a PTC is a little bit of a Band-Aid for that. But we do need to figure some real serious ideas about how we reform the market structure so that they properly incentivize that in a deregulated power market.
No, I mean, I think in a lot of ways, there's never been a better time to build nuclear in America with the PTC you're talking about, with an investment tax credit that I believe you build a nuke on a brownfield site with union labor, prevailing wage, and with a domestic supply chain, you're up to something like a 50% investment tax credit. You've got the PTC, exactly. The LPO has billions to shower. So I get this kind of frustration with, well, why the hell isn't it happening?
Well, so I believe, and don't quote me on I guess I'm on a podcast, so it will be quoted, but I believe that I'm not sure, but I think you actually have to make an election whether the ITC or PTC gets chosen for a new nuclear project. But as you just said, if you build on a coal power plant site in the United States, and the good and bad things about a nuclear project is that the prevailing wage standards, for example, you'll never not be able to meet those prevailing wage standards in a nuclear power build. So don't worry about that. And same thing with the domestic component stuff, because it actually works out. You'll literally get 50% of the price that you build, and not just overnight costs, including financing costs, right? On the day you commission your plant, you'll get 50% back. And if you're a muni, you'll get it as a tax credit, which could be, sold on the market and is transferable, and you'll get 90%, 80% on the dollar. But if you're a municipal utility, you will literally get a cash refund back from the IRS, right? For 50% of your power price. So just think about this. We have now, just without doing anything, right? We have split in half the total construction cost of a nuclear power plant just by doing that. And that is a perfect example when I was talking to Chris about us talking more as nuclear advocates, about not waiting 5 years, 10 years to the next plant. We have licensed power plants in multiple states. We have something like close to 12 gigawatts of new nuclear capacity that have been granted full COL. Some of them have been terminated by the licensee, but could probably be relicensed pretty quickly, that have been fully licensed by the NRC. They've gone through all their hearings. They have an environmental impact statement issued, right? We are literally their turnkey in terms of construction. And with a COL, you don't have to have another ASLB hearing, an Atomic Safety and Licensing Board hearing, right, for operations, right? You don't need an environmental impact statement. All that is done. The siting is done. The hearings are done. The EPZ is planned out. We are there waiting to be built. And we don't talk enough about them. And I think part of the issue is the SMR mania, or they're not SMRs. But that's a pretty damn good thing to try to start building. And I think sometimes we've so sort of gotten fixated on SMRs, which once again have their place and are going to be very important technologies, that we've forgotten those little sort of giants that exist in our midst that really could be transformative for getting those first couple new builds out. I'm kind of saying, let's crawl before we walk, before we run a marathon. And if we want to get into a place where this industry can really deliver for its customers, which it needs to, a couple 100 gigawatts of new nuclear capacity, let's start on what we've done before and try to translate it and choose these sites which now have literally zero regulatory burden in terms of getting a license and getting an environmental impact statement. Obviously, they're going to have to go, their construction will have to go through the CROP, Construction Reactor Oversight Program, to be monitored, but we really are in a good place on that. So that's my own lesson. My lesson is like, give the large modular reactors a little love. Let's give them a little love. Let's talk about them more. Let's understand their benefits as well as their disadvantages. Just like when we talk about SMRs, we should talk about their benefits and their disadvantages. That's all I'm saying. I'm not trying to put, rain on anyone's parade otherwise.
Yeah, for sure. Okay, we've got to leave it somewhere, James. We could talk for hours, and we probably will over the next God, who knows the time interval? But it's been great. Looking forward to getting this
I
out.
look forward to the deluge of hate I'm about to get from this episode. So
I think you've been pretty measured. I think you've been pretty measured. I'd be surprised.
I cannot even wait to what Twitter is going to do with me. But that's I guess the risk I take.
So be it. Bring it on. Okay, James. Thanks again.